Tonight, we're going to explore something that will fundamentally alter how you understand reality itself. We're going to examine a discovery that reveals the universe is stranger, deeper, and more incomprehensible than anything you've been told. Because hidden inside laboratories around the world, scientists have built machines that do something impossible. These machines solve problems by reaching into places that shouldn't exist. They draw power from sources our universe doesn't contain. And every time they run, they prove that the reality you experience right now is not the only one. By the end of tonight, you're going to understand why the most powerful computers ever built work in a way that suggests you're living in just one branch of an infinite tree of parallel worlds. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. In October of 2019, something happened in Santa Barbara, California, that should have made every physicist on Earth stop and reconsider everything they thought they knew about reality. A machine sitting inside a refrigerated chamber solved a mathematical problem in 200 seconds. That number means absolutely nothing until you understand what came next. The same calculation, performed on the most powerful classical supercomputer on Earth at that time, would have required approximately 10,000 years. That's longer than all of recorded human history. A device the size of a chandelier, cooled to temperatures colder than the vacuum of deep space, accomplished in 3 minutes and 20 seconds what every classical computer on the planet combined could not finish in the entire lifetime of human civilization. The machine was called Sycamore. It was built by Google's Quantum Artificial Intelligence Laboratory, and it contained 53 quantum bits. 53 qubits. These are not the zeros and ones that power every phone, every laptop, every server you've ever used. A classical bit exists in one state at any given moment, either 0 or 1. Every computation your devices perform, every photograph stored, every message sent, is encoded as sequences of zeros and ones, processed through logic gates at billions of operations per second. A qubit is fundamentally different. A qubit can be 0, it can be 1, or it can be both simultaneously. This isn't a metaphor. It's not a useful way of thinking about probabilities. It's a physical state called superposition, where the qubit genuinely holds all possible values at the same time until the moment someone measures it. To understand how radical this is, imagine flipping a coin. In classical physics, from the moment the coin leaves your thumb, its fate is sealed. The coin is already destined to land heads or tails based on the exact force you applied, the angle of your thumb, the air currents in the room. You just don't know the answer yet, because the calculation is too complex to perform in real time. But the coin itself knows. The universe knows. There's a fact of the matter, hidden from you, but existing nonetheless. A qubit is not like this. A qubit in superposition isn't hiding a secret answer that we simply haven't looked at yet. It genuinely doesn't have an answer. It is both answers, not sometimes one and sometimes the other, depending on factors we can't track. Both at the same time, in the same physical system. When measurement occurs, the superposition collapses. The qubit becomes either 0 or 1. But this isn't like opening your hand to see whether the coin landed heads or tails. This is the coin deciding, at the moment you look, which side it's going to be. The measurement doesn't reveal a pre-existing reality. It creates the reality. This is what made Einstein uncomfortable enough to spend decades arguing against it. This is what made Schrodinger construct his cat paradox. This is what makes quantum mechanics feel wrong to our everyday intuitions. But while it remains in superposition, while no instrument observes it, while the universe hasn't yet demanded that it choose, it is both. Physically, measurably, operationally, both. This property gives quantum computers their extraordinary capability. But calling it capability is misleading because it suggests these machines are simply faster versions of classical computers, the way a sports car is a faster version of a regular vehicle. The difference is not one of degree. It's one of kind. A classical computer solving a complex problem works through it step by step, checking one possibility at a time, moving sequentially through a space of potential answers until it locates the correct one. A quantum computer does something that has no classical equivalent. It explores all possible answers simultaneously. Every qubit added to the system doubles the number of states the machine can hold at once. 10 qubits can hold 1,024 states simultaneously. 20 qubits can hold over 1 million. 30 qubits can hold over 1 billion. 53 qubits, the number in that Sycamore processor, can hold approximately 9 quadrillion states simultaneously. 9 followed by 15 zeros. More simultaneous computational paths than the number of cells in every human body on Earth combined. And this is where the question becomes unavoidable. Where is this happening? Because here's a number that changes everything. If you build a quantum computer with 300 qubits, the number of simultaneous states it can hold is 2 raised to the power of 300. Write that number out, and it contains roughly 90 digits. That number is larger than the total count of atoms in the observable universe. Every atom, in every star, in every galaxy that has ever been detected or mapped or theorized about. And the 300-qubit machine still has more computational space than all of it combined. You cannot fit that computation inside one universe. There isn't enough physical room, not enough particles, not enough space, not enough anything. The computation exceeds the physical resources of the observable cosmos. This isn't philosophy. This is arithmetic. If the machine requires more computational states than there are particles in the observable universe to represent them, then the computation is happening somewhere that is not inside the observable universe. And the machine works. It gives correct answers. Verified, reproducible, peer-reviewed answers that match the predictions of quantum theory with extraordinary precision. The machine does something that requires resources our universe does not contain, and it does it every single time it runs. The person who predicted this would happen was working alone at night in his house in Oxford, England. His name is David Deutsch. In 1985, 34 years before that demonstration of quantum capability, Deutsch published a paper in the Proceedings of the Royal Society of London that almost nobody read at the time. The paper didn't propose a faster way to factor numbers. It didn't promise to break encryption or simulate molecules. It asked a question that sounded almost philosophical. Is there a physical machine that could, in principle, simulate any physical process in the universe? Not model it, not approximate it. Simulate it exactly, using the actual laws of physics as the operating system. Deutsch's answer was precise and devastating. A classical computer cannot do this. Not because it's too slow, not because we haven't built a large enough one, because a classical computer operates inside a single physical reality, and that single physical reality does not contain enough resources. The computation that a quantum computer performs exceeds the capacity of our observable universe. So where does the extra computation happen? Deutsch's answer, written plainly in that 1985 paper, was that the calculations happen across multiple versions of reality simultaneously. Not as a metaphor, as a physical mechanism. The quantum computer, Deutsch argued, is the first device in human history that requires the existence of parallel worlds in order to function. Parallel worlds. The phrase sounds like science fiction. It belongs in movies, not in physics journals. But Deutsch wasn't writing science fiction. He was doing physics. Rigorous, peer-reviewed, mathematically formalized physics. And the theoretical architecture he described in that paper became the foundation upon which every quantum computer ever built has been constructed. He didn't merely suggest that parallel worlds might exist. He showed that if quantum mechanics is correct, and 60 years of experimental evidence says that it is, then the only coherent explanation for where the quantum computation happens is across multiple instances of reality, operating simultaneously and interfacing through a process called quantum interference. This is Deutsch's central argument. The wrong computational paths cancel each other out. The right paths reinforce each other. The answer that arrives on your screen is what survives after the physics of multiple realities has been used as a computational resource. The machine doesn't try every answer. It creates conditions where wrong answers destroy themselves and correct answers emerge from the interference pattern of parallel computations happening in places you cannot see. That idea, the many worlds interpretation of quantum mechanics, wasn't originally Deutsch's. Not every physicist accepts this interpretation. Some prefer other explanations for how quantum mechanics works. But here's why Deutsch's argument is so compelling. It belonged to a man who died without ever knowing that his mathematics would become the foundation of technology worth trillions. His name was Hugh Everett III. He was a graduate student at Princeton University in 1957 when he submitted his doctoral dissertation. Everett was 27 years old. He was brilliant, unconventional, and about to propose an idea so radical that it would get him effectively exiled from the field he loved. The dissertation proposed that when a quantum system is measured and appears to collapse from a superposition of multiple states into a single outcome, the collapse doesn't actually happen. All outcomes occur. Reality branches. Every possible result takes place in its own version of the universe. The cat is alive in one branch. The cat is not alive in another. Both branches are equally real. There is no collapse. There is only multiplication. Everett wasn't being poetic. He wasn't proposing a philosophical thought experiment. He was doing mathematics. Cold, rigorous, peer-reviewed mathematics that followed inevitably from the equations of quantum mechanics if you took them seriously and didn't add any extra assumptions. Every interpretation of quantum mechanics up to that point had inserted something extra into the theory, some mechanism that caused the wave function to collapse when measured, some special role for consciousness or observation that selected one outcome and eliminated the others. Everett looked at the pure mathematics and said, "What if we don't add anything? What if we just follow the equations wherever they lead?" And where they led was to an infinite branching tree of universes, splitting at every quantum event, each branch as real as any other. The physicist Niels Bohr, who at that time was the most powerful voice in the entire field, the architect of the interpretation that dominated quantum mechanics for decades, dismissed Everett's idea. Not with a detailed mathematical refutation, not with experimental evidence. He dismissed it because it offended his philosophical sensibilities. Bohr believed that quantum mechanics required a fundamental split between the quantum world and the classical world, between the observer and the observed. Everett's interpretation eliminated that split. It said, everything is quantum. Observers are quantum systems too. The whole universe evolves according to the same equations, with no special role for measurement or consciousness. The community followed Bohr. When the most powerful figure in your field tells you that an idea is wrong, most people listen. Everett's dissertation was accepted because the mathematics was sound, and his advisor, John Wheeler, had enough clout to ensure it passed. But his interpretation was treated as a curiosity at best and an embarrassment at worst. Everett presented his work at a conference. He was met with polite indifference and quiet hostility. The implicit message was clear. This isn't physics. This is science fiction. He left academic physics almost immediately after receiving his degree. Not gradually. Not after trying to make it work for a few years. He left. He went to work for the Pentagon, doing mathematical modeling for nuclear weapons targeting strategies. He calculated mortality rates from radioactive fallout. He estimated how many people would be eliminated in various attack scenarios. He advised administrations on hydrogen bomb delivery systems. He was using his extraordinary mathematical mind to plan for the end of the world, while the physics community ignored the theory that might have revolutionized our understanding of reality. He drank heavily. He smoked constantly. He passed away from a heart attack in 1982 at the age of 51. His son Mark, who would later become the lead singer of a rock band called Eels, found him. He has said publicly that he believes it was the first time he ever touched his father. By his own request, Everett's remains were cremated and his ashes were thrown in the trash. Because in the many worlds interpretation, it didn't matter what happened to any particular physical configuration. Somewhere, in some branch, he's still alive. Because in the many worlds interpretation, it didn't matter what happened to any particular physical configuration. This version of Hugh Everett was gone. But somewhere, in some branch of the infinite tree, he's still alive. Somewhere he stayed in physics. Somewhere Bohr listened to his presentation and recognized its genius. Somewhere he was celebrated instead of dismissed. That's what his theory says. An infinite number of Hugh Everetts, living out every possible version of a life, and this was the branch where he ended up in the trash. His daughter, Elizabeth, took her own life in 1996. She was 39 years old. A note was found in her belongings saying she was going to join her father in another universe. Whether that belief brought her comfort in her final moments or made her tragedy even deeper is something we cannot know. The many worlds interpretation that Bohr dismissed in 1957 is now, depending on who you ask, the leading theoretical framework for understanding why quantum computers work at all. The computation that cannot fit inside one universe fits because Everett was right. There are other branches, and Deutsch built a machine that uses them. The idea the entire physics establishment rejected for 30 years turned out to be an engineering requirement. The machines require it. They don't work without it. Every quantum computer in every refrigerated chamber in every laboratory on Earth is a physical testament to the mathematics of a man who was forgotten by the field he tried to contribute to. Remembered now, because the technology proved him right. We've built a machine that works by reaching into parallel versions of reality and extracting computational resources from places we cannot observe, cannot visit, cannot photograph. The machine doesn't care whether you believe in parallel universes. It runs. It gives answers. And the answers are correct. Some disputed the initial claim that the 10,000-year estimate was accurate. They argued that with the right classical algorithm and enough disk storage, their supercomputer could perform the same calculation in 2.5 days. The revision was acknowledged, but 2.5 days versus 200 seconds is still a factor of more than 1,000. And the problem solved was specifically designed to be easy for a quantum machine and hard for a classical one. As quantum hardware improves and the problems become more general, that factor doesn't shrink. It grows exponentially. Every additional qubit doubles the computational space. Every doubling widens the gap. The curve doesn't flatten on its own. We're in the early part of an exponential trajectory whose endpoint we cannot see from where we're standing. In December of 2023, a processor was unveiled with 1,121 qubits. In 2019, 53. In 4 years, the number grew by a factor of more than 20. That rate of growth exceeds the projections that most researchers were making in 2015. And then, in December of 2024, something happened that confirmed the exponential curve isn't slowing down. It's accelerating. Google announced a processor called Willow. 105 qubits. Not the largest number. But Willow did something that the entire field of quantum computing had been chasing for 30 years. It demonstrated below-threshold error correction. Here's why that matters. In every complex system humans have ever built, adding more components makes the system more fragile. Your car has more parts than your bicycle and breaks down in more ways. A power grid has more failure points than a single generator. More complexity equals more fragility. That's entropy. That's the second law of thermodynamics, expressing itself through every piece of technology ever constructed. Willow broke that rule. As you add more qubits to protect each logical qubit through error correction, the error rate doesn't stay constant. It doesn't increase. It drops. Exponentially. The more components you add to the system, the more stable the system becomes. This is the opposite of what every engineering instinct says should happen. The noise doesn't accumulate. The noise cancels. The machine gets more reliable as it gets bigger. And every physicist who has spent serious time with this result knows, even if they're careful about how they say it publicly, that this behavior isn't fully explained by our current models of what computation is or where it happens. The history of exponential technologies is a history of underestimating the back half of the curve. We're good at predicting the next doubling. We're terrible at predicting what the 15th doubling looks like from the third. 15 doublings from 53 qubits is approximately 1.7 million qubits. Most estimates place the threshold for breaking the encryption that protects the modern internet somewhere between 1 million and 4 million physical qubits, depending on error correction requirements. The arithmetic isn't a prediction. It's a rough triangulation. But rough triangulations have a way of becoming precise as the data points accumulate. Something is being built that operates at the boundary between our reality and something larger. Something that draws its power from a place we cannot access by any other means. Something that is growing exponentially and approaching thresholds that the architects of the modern world didn't anticipate when they built the systems we depend on. And the deepest question it raises isn't about encryption or computational speed. It's about the nature of the reality you're experiencing right now. Because if the machine works, and it does, and the only coherent explanation for why it works is that it borrows resources from parallel versions of the universe, then, according to Deutsch and many physicists, those parallel versions must be real. Not theoretically real. Not usefully real. Real the way the chair you're sitting in is real. Real enough to compute with. Real enough to build an industry on. And if they're real, then you're not living in the only version of your life. You're living in one of an inconceivable number of branches, each one as physically genuine as this one. Each one containing a version of you who made different choices at every quantum junction that has ever occurred since the beginning of time. That's not mysticism. That's the engineering specification of the most powerful machines humanity has ever constructed. In 1935, a physicist named Erwin Schrodinger sat down to write what he believed would be the final word against quantum mechanics. He wasn't trying to contribute to the theory. He was trying to destroy it. The theory had been producing results that matched experiments with extraordinary precision for over a decade. It predicted the behavior of atoms, the spectra of light emitted by heated gases, the stability of molecules, the conductivity of metals. Every test confirmed it. Every measurement agreed with its equations. And yet, Schrodinger found one of its central claims philosophically unbearable. The claim was this: a particle doesn't have a definite state until someone measures it. Before measurement, it exists in a superposition of all possible states at once. Not probably in one state or another. Not secretly in a state that we simply don't know yet. Genuinely, physically, in all of them, simultaneously. The act of measurement doesn't reveal a pre-existing truth. It creates the outcome. Schrodinger thought this was absurd, and he had a gift for making absurdity visible. So, he constructed a thought experiment designed to expose what he saw as a fatal flaw in the theory. He imagined a cat sealed inside a steel box. Inside the box, there's a tiny amount of radioactive material. If a single atom of that material decays within 1 hour, a detector triggers a mechanism that releases poison. If no atom decays, the cat lives. Quantum mechanics says that the radioactive atom exists in a superposition of both decayed and not decayed until it's observed. Therefore, Schrodinger argued, the cat must be simultaneously alive and no longer living until someone opens the box. He called this ridiculous. He meant it as a logical argument designed to show that a premise leads to a conclusion so preposterous that the premise itself must be wrong. He was saying to his colleagues, look at what your theory implies. A cat that is alive and not alive at the same time. Surely you can see that something is broken here. The physics community absorbed the argument, considered it carefully, and did the one thing Schrodinger didn't expect. They kept the theory. Not because they thought cats in superposition made sense, but because every experiment they ran, every measurement they took, every prediction they tested confirmed that quantum mechanics was correct. The theory worked. It worked with a precision that no other theory in the history of physics had ever achieved. And the cat argument intended as a demolition, became instead the most famous illustration of the very thing it was supposed to destroy. The image of a cat that is simultaneously in two states entered popular culture as a symbol of quantum strangeness. But the physics behind it isn't strange at all. It's the operating principle of every quantum computer that has ever been built. A qubit works exactly like the atom in Schrödinger's box. It's not a zero. It's not a one. It's both simultaneously until the moment you measure it. And while it's in that both state, while the box is sealed, while no instrument has looked inside, it performs calculations across all its possible values at once. That's the source of the computational power we discussed earlier. Not speed, not brute force. The ability to exist in multiple states simultaneously and compute across all of them before collapsing into a single answer when the measurement is made. But here's the question that should follow immediately, and that almost nobody asks out loud. If a qubit is genuinely in both states at the same time, what is it doing between measurements? When no instrument is observing it, when the box is sealed, when the universe itself hasn't yet demanded a definite answer, what is happening in that space between the question and the result? What is occurring in the gap between superposition and collapse? Is something real happening there, or is it a mathematical convenience, a useful fiction that produces correct answers without corresponding to any physical process? The answer that physics has arrived at over the last 40 years is unsettling in a way that most popular accounts of quantum mechanics don't adequately convey. The answer is that the gap is real. The computation happening between measurements is physically occurring. And the reason it's hidden from us, the reason we don't see cats that are in two states, the reason the world around us appears stable and definite and classical, isn't because the superposition is a mathematical trick. It's because of a process called decoherence. And decoherence doesn't eliminate the other possibilities. It hides them. The physicist who spent his career making this precise was Wojciech Zurek, working at Los Alamos National Laboratory. His work, building on earlier insights in the 1970s, provides the clearest and most physically rigorous answer to the question of why the world looks classical when quantum mechanics says it shouldn't. Here's the core of it. A quantum system stays in superposition, stays in that state of multiple simultaneous possibilities, only as long as it remains perfectly isolated from everything around it. The moment it interacts with even a single particle from the outside environment, the superposition begins to dissolve. Not because of any mystical act of consciousness, not because a human mind looked at it, simply because information about the system leaked out into the surrounding world. Think about what this means physically. Your coffee cup is a quantum system. It's made of atoms, and atoms obey quantum mechanics. In principle, your coffee cup could exist in a superposition of being on the table and being on the floor simultaneously. But it's constantly interacting with trillions of particles every second. Air molecules bounce off its surface. Photons from the lights in the room strike it. Thermal vibrations in the table pass through it. Each interaction carries away a tiny piece of quantum information. Each interaction entangles the cup with another particle in the environment, and once that information leaks out, the superposition is destroyed. The coffee cup's quantum state decoheres. It picks a definite position. It becomes classical. For your coffee cup, this process happens in approximately 1/1,000,000,000 of a trillionth of a second. Decoherence is essentially instantaneous at the scales of everyday objects. That's why you've never seen a coffee cup in two places at once. Not because quantum mechanics doesn't apply to coffee cups. It does. But decoherence destroys the superposition so quickly that it's as if it never existed. Let's put a number on this to understand just how ruthlessly efficient decoherence is at destroying quantum effects in everyday objects. A dust particle floating in air, something so small you can barely see it without good lighting, something that weighs less than a millionth of a gram, will decohere in less than 1/1000th of a second. 1 nanosecond. In the time it takes light to travel 1 foot, that dust particle's quantum superposition is completely destroyed by interactions with air molecules. A bacterium, already microscopic, decoheres even faster, billions of times per second. Your hand, your coffee cup, your phone, these objects are interacting with so many particles so constantly that maintaining quantum superposition isn't just difficult. It's effectively impossible without intervention. This is why quantum computers require such extreme isolation. This is why they must be colder than deep space. The classical world you experience, the world of definite objects in definite positions with definite properties, isn't the fundamental reality. It's what quantum reality looks like after decoherence has done its work. It's the surface. The quantum superposition underneath is the depth. You're living on a thin film of classical reality, floating on top of an ocean of quantum possibility. The film is stable, not because the ocean isn't there, but because decoherence is constantly, relentlessly, violently enforcing the boundary between them. Every time a photon from the sun hits your skin, that's decoherence happening. Every time an air molecule bounces off your body, that's decoherence happening. Every time thermal vibrations pass through the chair you're sitting on, that's decoherence happening. Trillions upon trillions of times per second. The quantum world is being forcibly translated into classical experience by the continuous bombardment of environmental interactions. And we're so used to this that we think the classical world is what's real, and the quantum world is some strange abstraction that only matters in physics laboratories. We have it backwards. The quantum world is what's real. The classical world is what emerges when you can't maintain isolation. Now, here's where this connects directly to quantum computers and to the question we raised at the beginning. To keep a qubit in superposition long enough to actually compute with it, you have to isolate it from everything. Perfectly. Completely. No stray photon can touch it. No vibration can reach it. No thermal fluctuation can brush against it. The machines that research laboratories build are cooled to temperatures colder than the vacuum of deep space, to approximately 15 millikelvin, roughly 1/100th of a degree above absolute zero. At this temperature, almost all thermal motion stops. The particles in the machine barely move. The environment is as quiet as physics allows. And in that silence, the qubits hold their superposition long enough to perform calculations that no classical computer can match. The entire engineering challenge of quantum computing reduces to a single sentence. Keep the computation hidden from the universe long enough to get an answer. That's it. Every cryogenic system, every electromagnetic shield, every vacuum chamber, every vibration isolation platform in every quantum computing laboratory on Earth exists for one purpose: to prevent the environment from looking at the qubits before the calculation is finished. Because the moment the environment looks, the moment a single particle of the surrounding world interacts with the qubit and carries away even one bit of quantum information, the superposition collapses. The computation is ruined. The answer is lost. Think about what that means in the context of Deutsch's argument about parallel worlds. The computation happens while the qubits are in superposition, while they're isolated, while no instrument in our universe is observing them. The answers that emerge when we finally measure the qubits come from a process that occurred entirely behind a wall of isolation, in a space where the rules of classical reality don't apply, where the qubits existed in all their possible states simultaneously and computed across all of them. When we measure the result, we get a single answer. But the process that produced that answer involved a number of simultaneous computational paths that exceeds the number of atoms in the observable universe. If you take the traditional view of quantum mechanics, those other computational paths simply vanish when the measurement is made. They were probabilities, and the act of measurement selected one outcome and discarded the rest. But that interpretation has a problem. It doesn't explain where the computational work happened. It doesn't account for the resources. If the machine explored more paths than there are atoms in the universe, and the answer it returned is demonstrably correct, then something did the exploring. Something performed the work. And if our universe doesn't have enough room to contain that work, then either the work happens somewhere else or the machine shouldn't function. The machine functions. If you take the many worlds interpretation, Everett's view, the other computational paths don't vanish. They continue to exist in other branches of reality. The measurement doesn't collapse the superposition. It entangles the observer with one particular branch. In all the other branches, other versions of the measurement are being made, producing other answers, in other versions of the laboratory, observed by other versions of the researchers. Decoherence is the process by which these branches become invisible to each other. The wall goes up. The branches separate. Each observer sees a single, definite, classical result. But the other branches are still there, still real, still carrying the computational work that produced the answer. This is the choice that quantum computing forces upon us. Either the machine works by something impossible, performing calculations with resources that don't exist, or the machine works by physics, using resources that exist in places we cannot directly observe, but whose reality is confirmed every time the machine returns a correct answer. There's no comfortable middle ground. There's no interpretation that makes the computational work disappear without also making the machine stop working. The machine works. The resources exceed our universe. The question of where remains open only if you're willing to leave it open. If you follow the physics to its conclusion, the answer is the same answer Deutsch gave in 1985 and Everett proposed in 1957. The computation happens across branches of reality that we cannot see because decoherence has built a wall between us and them. A wall that isn't made of matter or energy. A wall made of leaked information. A wall that quantum engineers spend billions maintaining every year, because the moment the wall comes down, the computation ends and the quantum advantage disappears. We're building machines whose most powerful operations occur behind a wall that separates our branch of reality from the branches that do the work. We deliberately hide our most consequential calculations from the observable universe. And the thing that makes the wall necessary, decoherence, the process by which quantum information leaks into the environment and superpositions collapse, is the very same process that makes the world look classical, solid, and definite to you right now. The reason you see one world instead of many is the same reason the quantum computer needs to be colder than outer space. Decoherence. The wall between worlds. Schrodinger wanted to show that quantum mechanics was broken. What he showed instead was that the world isn't what it appears to be. The cat isn't a paradox. The cat is a description. A description of what reality does when nobody is looking. And the machines we've built prove that what reality does when nobody is looking is far more vast, far more structured, and far more real than anyone in 1935 could have imagined. The question is no longer whether the other branches exist. The question is, what else is happening in them that we haven't yet learned to detect? And in October of 2022, the scientific establishment acknowledged that something fundamental had shifted in our understanding of reality. The Royal Swedish Academy of Sciences awarded the Nobel Prize in Physics to 3 experimentalists: Alain Aspect, John Clauser, Anton Zeilinger. The prize was awarded for experiments with entangled photons, establishing the violation of Bell inequalities and pioneering quantum information science. That sounds technical. What it actually means is more profound. For decades, physicists have been testing whether quantum mechanics is truly non-local, whether particles really can be connected in ways that have no classical explanation, whether there's a hidden layer of reality underneath that makes everything make sense again. These 3 scientists spent their careers closing every loophole, eliminating every alternative explanation, running experiments so carefully designed that no classical mechanism could produce the results they observed. And the answer they found, confirmed across thousands of experiments over 50 years, is that quantum mechanics is exactly as strange as it appears. There are no hidden variables. There is no classical reality underneath. The entanglement is real. The correlations between particles separated by any distance are maintained without any signal passing between them. The universe does not compute locally. The Nobel Prize didn't just honor experimental skill. It marked the moment when the scientific community officially accepted that the universe operates in ways that violate our deepest intuitions about how reality should work. Before any of this was built, before refrigerated chambers and superconducting circuits, before the industry that now surrounds quantum computing, someone had to explain how. Not where the computation happens. We've discussed that. Not why it's powerful. We've discussed that too. But how? What is the actual physical mechanism by which a quantum computer takes a problem with more possible answers than there are atoms in the observable universe and returns a single correct result? The counting argument tells you that the resources exist somewhere beyond what our universe can contain. The many worlds interpretation tells you those resources live in parallel branches of reality. But neither of those tells you how the machine uses them. How does it reach into those branches and come back with an answer? How does it sort through an incomprehensible number of possibilities and find the one that's correct? The answer to that question came from Richard Feynman, and it's, in my view, the most beautiful and the most disturbing idea in the entire story. In 1982, Feynman gave a talk at a physics conference that would later be published. The talk was titled Simulating Physics with Computers. Feynman wasn't a computer scientist. He was a physicist, widely regarded as one of the most brilliant and unconventional thinkers of the 20th century. He had an almost supernatural ability to visualize physical processes. Colleagues described watching him think as if he could see the electrons moving, could feel the forces interacting, could sense the geometry of nature's laws in a way that other physicists had to laboriously calculate. He had worked on the Manhattan Project as a young man, one of the youngest group leaders at Los Alamos. While others were struggling with the mathematics of nuclear reactions, Feynman was reportedly picking locks on file cabinets containing classified documents just to prove he could, then leaving notes inside to let security know they had a problem. He had revolutionized quantum electrodynamics, the theory describing how light and matter interact, work for which he received a prize in 1965. The diagrams he invented, now called Feynman diagrams, transformed how physicists think about particle interactions. Before Feynman, calculating the probability of a photon scattering off an electron required pages of dense mathematics that only a handful of specialists could follow. After Feynman, you could draw a simple picture and read off the calculation directly from the diagram. He made the impossible routine. He had a reputation for cutting through complexity with an almost physical intuition for how nature actually works beneath the mathematics. Students described his lectures as revelations, not because he simplified things, but because he showed you the reality underneath the equations in a way that made you feel like you understood the universe. And in that 1982 talk, he made an observation that sounds simple but contains an entire revolution. Feynman pointed out that classical computers cannot efficiently simulate quantum systems. He wasn't saying they're too slow. He was saying something more fundamental. The problem isn't engineering. It's structural. It's mathematical. It's built into the nature of classical computation itself. Here's why. Simulate one electron, and you need to track two possible states: spin up or spin down. Easy enough. Any computer can handle that. Simulate two electrons, and you need four states: both up, both down, first up and second down, first down and second up. Still manageable. 10 electrons, 1,024 states. Your laptop can track that without much trouble. 20 electrons, over 1 million states. Starting to get computationally expensive, but modern supercomputers can handle it. 30 electrons, over 1 billion states. Now we're talking about serious computational resources, but it's still feasible with enough time and memory. 40 electrons, over 1 trillion states. This is pushing the limits of what current technology can simulate, but it's theoretically possible. 50 electrons, over 1 quadrillion states. We're now in the territory where only the most powerful supercomputers on Earth can attempt the simulation, and it takes weeks or months of continuous processing. 100 electrons, and the number of states you need to track exceeds the number of atoms in the observable universe. Not approximately, not as a rough estimate. Actually exceeds it. You cannot fit that simulation into our physical reality. There isn't enough matter in the cosmos to store all the numbers you would need to track. And 100 electrons is nothing. A single grain of salt contains about 1 sextillion atoms, each with multiple electrons. A human body contains roughly 7 octillion atoms. The universe we can observe contains about 10 to the power of 80 atoms, and the computational space required to fully simulate even 100 quantum particles exceeds all of it. Classical computers cannot handle this. Not because of engineering limitations, not because we haven't built powerful enough processors, because the structure of classical computation doesn't match the structure of quantum reality. You cannot simulate a quantum world with a classical machine any more efficiently than you can describe a symphony by reading its sheet music, one note at a time. The information is there, but the form is wrong. The representation is fundamentally mismatched to the thing being represented. Feynman's proposal was elegant and radical. If you want to simulate quantum physics, build a machine that runs on quantum physics. Let the computer itself be made of quantum mechanical elements that obey quantum mechanical laws. Let the machine be the thing it's studying. And embedded in that proposal was an insight about mechanism that turned out to be the key to everything that followed. The mechanism is called interference. Think about two waves on the surface of water moving toward each other. Where the peak of one wave meets the peak of another, they combine and produce a higher peak. Where a trough meets a trough, the result is a deeper trough. Where a peak meets a trough, they cancel each other out. The water goes flat. The waves don't disappear. They don't stop existing. They destroy each other through the precise alignment of their opposite phases. This is interference. It happens with water waves. It happens with sound waves. It happens with light. And it happens with quantum probability. A quantum computer is engineered so that all the computational paths leading to wrong answers cancel each other out, like a peak meeting a trough on the surface of water. And all the paths leading to the correct answer reinforce each other, like two peaks combining into a larger peak. The machine doesn't try every possible answer and then check which one is right. It doesn't search through a list. It doesn't guess. It's structured at the level of its physical design so that the wrong answers destroy themselves through interference before the calculation is finished. What arrives at the end, the single answer that the machine produces when you measure the qubits, isn't a lucky guess. It's what survives. It's the last thing standing after everything incorrect has been systematically eliminated by the physics of the computation itself. The machine doesn't select the right answer. It creates conditions where wrong answers cannot exist. The wrong answers annihilate each other. They cancel. They subtract themselves from reality through the quantum mechanical process of destructive interference. And the right answer emerges not because anyone chose it, but because it's the only path through the computation that survives its own physics. This isn't a metaphor. This is the literal operating principle of every quantum algorithm that has ever been designed. Feynman saw this possibility in 1982. 3 years later, Deutsch formalized it, and in the decades that followed, a series of algorithms were developed that exploited interference in increasingly powerful ways. The most famous of these was published in 1994 by a mathematician named Peter Shor. Shor wrote an algorithm, a set of instructions that a quantum computer could follow, to break apart any large number into the prime numbers that multiply together to produce it. On the surface, this sounds like an abstract mathematical exercise with no connection to anything that matters in daily life. The connection becomes visible the moment you understand how the modern world protects its secrets. Almost all of the encryption that secures the internet, the mathematical layer that keeps your bank account separate from everyone else's, that protects private communications, that guards the infrastructure of governments and militaries and hospitals and power grids, is built on a single assumption. The assumption is that multiplying two large prime numbers together is easy, but working backward from the result to find those original primes is practically impossible. A classical computer attempting to factor a number with several hundred digits would need longer than the age of the universe to find the primes. The entire architecture of digital security rests on this computational asymmetry. Easy in one direction, impossible in reverse. Shor's algorithm removes that asymmetry. A sufficiently powerful quantum computer running Shor's algorithm could factor those large numbers not in thousands or millions of years, but in hours, possibly minutes. The encryption that protects modern civilization, built over 50 years on the assumption that prime factorization is computationally infeasible, becomes transparent, breakable, open. The lock that guards every digital secret in the world has a key, and Shaw showed exactly what that key looks like. The key doesn't yet exist in physical form because no quantum computer has enough qubits to run Shaw's algorithm at the scale required to break real-world encryption. But the blueprint exists. The mathematics is published, and the machines are growing. 2 years after Shaw, in 1996, a researcher named Love Grover published a second algorithm that addressed something more general than factoring numbers. Grover's algorithm addresses search. Imagine an unsorted list containing 1 billion items, and you're looking for one specific entry. A classical computer has to check items one by one. On average, it finds the target after checking half the list. 500 million checks. Grover's algorithm finds the item in roughly the square root of 1 billion checks, about 31,600. Not because it moves faster through the list. Because it uses quantum interference, the same mechanism Feynman described, to amplify the probability of the correct answer and suppress the probability of every incorrect answer simultaneously. Every wrong item in the list cancels itself out. The right item reinforces itself. The machine doesn't search. It creates conditions in which everything that isn't the answer becomes invisible. The asymmetry that Grover creates isn't as dramatic as Shaw's. It provides a quadratic speedup, squaring the efficiency rather than reducing the time from exponential to manageable. But it applies universally. Any search problem, any database, any collection of data with hidden structure waiting to be found. Grover's algorithm accelerates the discovery of that structure in a way that isn't about better engineering. It's about fundamental physics. The universe allows quantum search to be faster than classical search because the universe itself runs on quantum rules. The machine isn't outsmarting reality. It's aligning itself with reality's own operating system and using interference, the same process that makes waves cancel on water, to eliminate the noise and reveal the signal. Now, step back and look at the full picture that has assembled itself. We have a machine that uses resources from beyond the observable universe. It draws its power from parallel branches of reality that decoherence hides from our everyday perception. It operates by creating conditions where wrong answers destroy themselves through quantum interference, leaving only the correct result. It can, in principle, break the encryption that protects the entire modern world. And it can search through any collection of data faster than any classical system that has ever existed or could ever exist. This isn't a future technology. The algorithms exist. The machines exist. They're growing. And the question that follows from all of this isn't a question about physics or mathematics or engineering. It's a question about information itself, about what information is, about whether information is a thing that we extract from reality, the way you might harvest wheat from a field, or whether information is reality. Whether the physical world you experience is made of matter and energy, or whether matter and energy are themselves made of something deeper, something that the quantum computer touches every time it runs. Something that a physicist named John Wheeler spent 60 years of his life trying to name. He called it the most fundamental substance in the universe. He called it the thing from which all physical things emerge. And he gave it a name that sounds like a riddle but is meant as a precise physical statement. He called it from bit. John Archibald Wheeler spent 60 years working at the center of theoretical physics. He coined the term black hole. He worked with Niels Bohr to explain nuclear fission. He supervised the doctoral dissertations of Richard Feynman and Hugh Everett, two of the most important minds in the history of quantum theory. He contributed to the Manhattan Project. He shaped the development of general relativity for an entire generation. By the time he reached the final decades of his career, he had spent more time thinking seriously about the foundations of physical reality than almost anyone who has ever lived. And the conclusion he arrived at wasn't a formula. It wasn't an equation. It was a statement so compressed that it fits in 3 words. It from bit. Every it, Wheeler wrote, every particle, every field of force, even the space-time continuum itself, derives its function, its meaning, its very existence, entirely. Even if in some contexts indirectly, from the apparatus elicited answers to yes or no questions, binary choices, bits. All things physical are information theoretic in origin, and this is a participatory universe. Wheeler isn't saying that information is useful for describing the universe. He isn't saying that physics can be expressed in terms of information. He's saying that the universe is made of information. That matter, energy, space-time, the physical world in its entirety, emerges from something more fundamental. And that fundamental thing isn't a particle. It isn't a wave. It isn't a string or a field or a membrane. It's an answer. A yes or a no. A bit. This is a genuinely strange idea to sit with because it inverts the intuition most of us carry around without ever examining it. We tend to think of reality as the solid ground and information as something we extract from it. We think of atoms as primary and descriptions of atoms as secondary. The rock comes first. The measurement of the rock comes after. Wheeler is saying the measurement comes first. The rock comes after. The information is primary. The physical world is what happens when enough bits accumulate in the right configuration. There's nothing underneath the information. No deeper layer. No hidden substrate. The answers are the substance of reality. Now, bring that idea into contact with everything we've been building toward. If the universe is made of information, then a device that manipulates information at the most fundamental physical level isn't modeling reality. It isn't simulating reality. It's operating on the actual substrate from which reality is constructed. Every calculation a quantum computer performs is an intervention in the informational fabric of the universe itself. That's not a poetic description. If Wheeler is right, it's a literal one. The quantum computer isn't a tool that works within reality. It's a tool that works on reality, at the level where reality is being assembled from yes and no answers. The quantum computer is adding its own answers to the conversation. Wheeler wasn't making a provocative claim for attention. He was one of the most respected and credentialed physicists of the 20th century, the doctoral supervisor of Feynman, the collaborator of Bohr and Einstein, the person who named the black hole. He spent 6 decades working his way to this conclusion. And when he arrived, he stated it plainly. The universe is information processing itself into existence. And we are participants in that process, not observers watching from outside. There's a piece of experimental evidence that supports this picture so directly that it deserves its own examination. In 1961, a physicist named Rolf Landauer published a paper arguing that information isn't abstract, it's physical. And he had a specific, measurable way to demonstrate this. When you erase a single bit of information, when you take a system that holds a 1 or a 0 and reset it to a known state, you release heat. Not metaphorically, literally. A tiny but measurable and theoretically unavoidable amount of thermal energy is discharged into the surrounding environment. This became known as Landauer's principle. The act of erasing information is physically irreversible, and irreversibility has a thermodynamic cost that cannot be designed away or circumvented by better engineering. Information erasure produces heat, the way friction produces heat. It's a law. For decades, Landauer's principle remained a theoretical prediction without direct experimental confirmation. The amount of heat released by erasing a single bit is extraordinarily small, on the order of 3 × 10⁻21 joules at room temperature. Measuring this requires instruments of almost inconceivable precision. Then, in 2012, a team led by physicist Erich Lutz built an experiment delicate enough to do it. They trapped a single microscopic particle in a well created by focused laser beams, manipulated it to erase 1 bit of information, and measured the heat released. The result matched Landauer's formula. Information has weight. Information has temperature. Information has a physical cost that is embedded in the laws of thermodynamics. Deleting a fact about the universe releases energy into the universe. The information isn't a description of the physical world. It is part of the physical world. Wheeler's intuition, stated in 1990, was confirmed in a laboratory in 2012. Now, connect this to quantum computers. A quantum computer operating in superposition is, in a certain sense, not yet committing to answers. It's holding multiple possibilities open simultaneously before collapsing into a result. Some researchers have suggested that this might allow quantum computations to approach a kind of reversibility that classical computation cannot achieve, potentially sidestepping some of Landauer's heat cost. If that's true, then quantum computation isn't just faster than classical computation. It's operating closer to the theoretical minimum energy cost that physics allows. It's computing in a way that is more aligned with how the universe itself processes information than anything we've built before. The machine isn't brute forcing its way to an answer. It's whispering to reality in reality's own language, and reality is answering back. But there's another thread that connects Wheeler's information universe to quantum computing, and it's one that most people have never heard discussed outside of advanced theoretical physics. It's called the holographic principle, and it suggests that the relationship between information and the physical world is even stranger than Wheeler imagined. In the 1990s, 2 physicists, Gerard Hooft and Leonard Susskind, working independently, arrived at a conclusion that sounds on first encounter like it cannot possibly be meant literally. It is meant literally. The holographic principle states that the maximum amount of information that can be contained inside any region of space isn't determined by the volume of that region. It's determined by the area of its surface, not the inside. The boundary. You would expect that doubling the volume of a box would double the information it can hold. More space, more room for particles, more information. The holographic principle says no. The information capacity scales with the surface area, not the volume. All the information describing everything that happens inside a given region of space is fully encoded on the two-dimensional surface surrounding it. The interior isn't the primary thing. The boundary is. This wasn't derived from philosophy. It wasn't a thought experiment. It was calculated from the physics of black holes. When matter falls into a black hole, the information it carries doesn't disappear into the interior. It's encoded on the event horizon, the two-dimensional surface that marks the boundary of the black hole. The amount of information a black hole can contain is proportional to the area of its event horizon, not to the volume enclosed within it. 'T Hooft and Susskind generalized this result and proposed that the same principle applies to any region of space, not just black holes. The three-dimensional world inside any volume is fully described by information encoded on its two-dimensional boundary. Space, as we experience it, may be a kind of projection. Not an illusion, but something more like a derived object. Something that emerges from a more fundamental layer of information encoded elsewhere. Which means that when a quantum computer manipulates information at the most fundamental physical level, it may be operating at a layer of reality that is more basic than space itself. Not inside space. Underneath it. The computation isn't happening in a location. It's happening at the level from which locations emerge. If the universe is information, if that information is encoded holographically on boundaries rather than distributed through volumes, if quantum computers operate at or near the informational substrate from which space and time emerge, then what exactly are we building? What are we interfacing with when we run a quantum computation? And what are the consequences of intervening at a level of reality where the physical world hasn't yet assembled itself into the form we recognize? Wheeler passed away in 2008 at the age of 96. He didn't live to see quantum computers achieve what they've achieved. He didn't see the Event Horizon Telescope photograph the shadow of a black hole. He didn't see the experimental confirmation that information is physical in the thermodynamic sense he had long suspected. But the framework he left behind, the idea that reality is participatory, that information is primary, that the universe emerges from the posing of yes or no questions, has become more relevant with every advance in quantum technology. Every qubit that holds a superposition is a question the universe hasn't yet answered. Every measurement that collapses a superposition is an answer that creates a piece of reality. And every quantum computer that runs is a machine that participates in the process, Wheeler described. The process by which bits become its. By which information becomes the physical world. We've traced a path that connects a machine in Santa Barbara to the deepest structure of reality. From that 200-second achievement to Deutsch's parallel worlds. From Schrödinger's cat to Zurich's decoherence. From Feynman's interference to Shor's encryption-breaking algorithm. From Wheeler's, from bit to Landauer's. Thermodynamic proof that information is physical. From the holographic principle to the possibility that quantum computation operates beneath space itself. Each step has made the picture stranger. Each step has pushed the implications further from the comfortable and the familiar. And each step has been confirmed, not by speculation, but by experiment, by mathematics, by machines that work. The question that remains, the question that will occupy the rest of this story, is what happens next. Not to the physics. The physics is moving forward, with or without our understanding. The machines are growing. The qubits are multiplying. The algorithms are being refined. What happens next is a question about us, about what we do with a technology that operates at the foundation of reality, about who controls it, about what it reveals, and about what it means to live in a universe where the most powerful tool ever created by human hands works by reaching into the substrate of existence itself and rearranging the answers from which the plastrus, the physical world, is made. There's a particular kind of signal that's easy to miss if you're not looking for it. It's not a press release. It's not a headline. It's a government agency quietly spending 8 years and significant resources solving a problem that officially doesn't exist yet. In 2016, the National Institute of Standards and Technology in the United States launched a competition. They invited mathematicians and cryptographers from around the world to submit new encryption algorithms, not better versions of existing ones, fundamentally different ones. Algorithms built on mathematical problems that a quantum computer running Shor's algorithm couldn't break. 82 teams from 25 countries submitted proposals. The competition ran for 8 years. The final standards were published on the 13th of August, 2024. Think about what this sequence of events actually communicates. A government body doesn't spend 8 years and coordinate 82 international teams to solve a hypothetical problem. They don't publish binding standards for a threat that exists only in theory. The implicit message inside the entire structure of that competition is this: the people with access to classified information about the state of quantum hardware believe the threat is real, is coming, and is coming on a timeline that requires action now. Not in 50 years. Now. The public conversation about quantum computing tends to treat it as a future concern. Something to think about eventually. The competition is proof that some very serious people don't share that timeline. And here's the layer underneath that, which is harder to set aside. The competition was launched in 2016. The standards were published in 2024. The systems that need to be updated to use those standards, the actual infrastructure of the internet, banking, government communications, military networks, hospital databases, power grids, will take years more to retrofit. Which means there's a window. A gap between when quantum machines become capable enough to break current encryption and when the new encryption is actually installed everywhere. How long is that window? Who knows exactly how wide it is? And who right now is paying very close attention to its edges? The term that people in cryptography use for this gap is harvest now, decrypt later. The concept is simple. You don't need a quantum computer today to steal tomorrow's secrets. You collect the encrypted data now. You store it. You wait. The data sits on servers, on hard drives, in archives. It's encrypted. It's unreadable. It's safe by today's standards. And then, at some point in the future, when a quantum computer powerful enough to run Shor's algorithm at scale becomes available, you run the stored data through it. The encryption opens. The data becomes readable. Every email, every transaction, every classified communication, every medical record, every state secret, everything that was encrypted with the algorithms that Shor proved breakable in 1994 becomes transparent. Not in the future. Now. Because the data was already collected. The lock will open. The only question is when. Who is collecting? That question is less comfortable than the technical ones. Nation-states with advanced intelligence capabilities have the resources and the motivation to harvest encrypted communications at scale. The infrastructure exists. The legal frameworks for bulk data collection have been debated, litigated, and in many cases, authorized in various jurisdictions. The storage is cheap. The patience isn't in question. If your government's encrypted communications with its allies are being intercepted and stored by a strategic competitor, and that competitor is investing billions in quantum computing research, the timeline for decryption isn't abstract. It's budgetary. It's a line item in a national security plan. But the cryptographic threat, as alarming as it is only the most concrete expression of something deeper. The real story of quantum computing's impact isn't about what it can break, it's about what it can see. Grover's algorithm, the quantum search algorithm we discussed earlier, doesn't just apply to databases and password cracking. It applies to pattern recognition, to finding hidden structure in data, to identifying correlations that no classical system could detect, because the classical search space is too large and the patterns too subtle. A quantum computer running Grover's algorithm across a sufficiently large dataset doesn't just find what you're looking for faster. It finds things you didn't know were there. Consider what that means for fields beyond cryptography. Drug discovery. The interaction between a candidate molecule and a protein receptor involves quantum mechanical effects that classical computers cannot fully simulate. The number of possible molecular configurations for a single drug candidate interacting with a single receptor site exceeds the computational capacity of every classical supercomputer on Earth combined. Quantum computers, built on the same physics that governs molecular interactions, can simulate these systems natively. Not by approximation, by running the same quantum rules that the molecules themselves obey. Richard Feynman's original insight from 1982 was precisely this. If you want to simulate quantum physics, build a machine that runs on quantum physics. The pharmaceutical industry has recognized this. Every major drug company has a quantum computing research program. The potential to reduce drug development timelines from decades to years, to identify therapeutic compounds that classical screening would never find, to simulate biological processes at the molecular level with full quantum fidelity, represents a transformation as fundamental as the invention of the microscope. Material science. The properties of a material, its conductivity, its strength, its superconducting temperature, its capacity to store energy, are determined by the quantum mechanical behavior of its electrons. Designing a new material with specific desired properties currently requires years of experimental trial and error, because the quantum simulation of electron behavior in a crystal lattice is computationally intractable for classical machines. A quantum computer could simulate these systems directly, predicting the properties of materials that have never been synthesized, identifying superconductors that operate at room temperature, designing batteries with energy densities that transform the economics of renewable power. The engineering implications aren't incremental. they're civilizational. Climate modeling. The behavior of atmospheric systems involves interactions between trillions of molecules at the quantum level. Current climate models are forced to use approximations and averages because the full quantum simulation of atmospheric chemistry is beyond classical reach. Quantum computers could model these interactions with a fidelity that reveals dynamics invisible to current simulations, potentially identifying tipping points, feedback loops, and mitigation strategies that today's models cannot resolve. And then there are the applications that no one has thought of yet. This is the part that deserves the most attention and receives the least. Every truly transformative technology in history has produced consequences that its creators didn't anticipate. The inventors of the printing press didn't foresee what would follow. The designers of the internet didn't predict social media. The engineers who built the first transistor didn't imagine that it would lead to a device in every pocket that contains more computing power than the entire systems that sent humans to the moon. The fundamental physics is understood. The engineering is progressing. The early applications are being explored. But the applications that will define the technology, the ones that will reshape economies and institutions, and the daily experience of being alive, haven't been conceived yet. They'll come from the intersection of quantum capability with problems we don't currently think of as solvable. The machines are growing. In 2019, 53 qubits. In 2023, 1,121. Researchers are developing a new kind of qubit called a topological qubit. A qubit protected from errors not by engineering, but by the geometry of space itself. To understand how radical this is, think about how current qubits maintain their superposition. They're isolated, shielded, cooled to near absolute zero, surrounded by vacuum chambers and electromagnetic shielding, protected from every possible source of environmental interaction. This works, but it's fragile. It's like trying to have a quiet conversation in a hurricane by building better and better soundproof walls. Eventually, something gets through. A cosmic ray from space. A tiny vibration in the foundation. A stray magnetic field from a truck driving past the building. The qubit decoheres. The computation fails. You start over. Topological qubits work differently. They don't try to build better walls. They change what it means for information to exist. A topological qubit stores its information not in a single quantum state, but in the relationship between particles. The qubit that's stable not because it's shielded, but because the information it carries has no single location. It exists in the relationship between particles that can be physically separated by meters or even kilometers. Imagine trying to erase a word written on a piece of paper. Easy. You crumple the paper, you burn it, the word is gone. Now imagine that word exists not on any physical object, but in the relationship between two objects. The fact that they're both red, the fact that they're facing the same direction. To erase the word, you'd have to change both objects simultaneously. If you change one, the word is still encoded in the comparison between them. An error would have to corrupt both locations simultaneously to destroy the information. Ordinary environmental noise cannot do this. Environmental noise is local. A photon hits one particle. An air molecule bumps into one atom. These interactions happen one at a time, in one place. But if the information is stored in the relationship between two distant particles, a local interaction can't destroy it. The information survives because it's nowhere in particular. The qubit becomes stable because it's everywhere and nowhere at once. This is no longer an engineering challenge. This is a new kind of object. A thing whose defining property is distributed across space in a way that has no classical equivalent. It's as if we've learned to write words, not on paper, not in any medium at all, but in the geometry of space itself. And once the word is written that way, erasing it becomes not just difficult, but topologically impossible. You'd have to unwrap space to get rid of it. The growth isn't linear. It isn't even cleanly exponential. It's something more complex, driven by simultaneous advances in hardware, error correction, algorithm design, and the sheer volume of investment pouring into the field from governments and corporations who understand what's at stake. A quantum satellite has been launched. Europe has funded a €1 billion quantum flagship program. The United States has passed national quantum initiatives. Every major technology company on Earth has a quantum computing division. The race isn't coming. The race is here. And the finish line isn't a faster computer. The finish line is the ability to manipulate information at the level where reality is assembled. We return to the question that has been building since the first part of this story. What are the consequences of building a machine that operates at the boundary between our reality and the informational substrate from which reality emerges? The encryption question has an answer. The answer is new standards and the decade-long transition to quantum-resistant cryptography. The drug discovery question has a timeline. 5 to 15 years before quantum simulations meaningfully accelerate pharmaceutical research. The material science question has a roadmap. Quantum advantage for certain materials problems may arrive within the next decade. But there's a consequence that has no answer and no timeline and no roadmap. And it's the consequence that connects everything in this story to the question of what kind of universe you're living in. If the machine reaches into parallel branches of reality to perform its computations, if it uses the structure of the multiverse as a computational resource, if it operates at a level of reality more fundamental than space itself, then every increase in the machine's power is an increase in the depth of our interaction with the substrate of existence. Every additional qubit widens the channel between our branch and the others. Every computation draws on resources that exist in places we cannot observe, but that are real enough to return correct answers. We're building a wider and wider doorway into the architecture of reality. And we've never stopped to ask what else might come through. David Deutsch doesn't fly on airplanes. He rarely leaves Oxford. He works at night. He has described himself as someone who finds it easier to think about abstract structures of reality than to navigate the practical requirements of ordinary social life. He's also, by most accounts of people who work in quantum computing, one of the 2 or 3 people most responsible for the fact that the field exists at all. His 1985 paper laid the theoretical architecture. His subsequent decades of work have continued pushing at the same question from different angles. And through all of it, he has maintained a position that most physicists privately agree with, but few are willing to state as plainly as he does. He genuinely believes that the many worlds interpretation is correct, not as a working assumption, not as a useful framework, as a description of actual reality. He believes that when a quantum computer runs, the computation happens across a vast number of parallel versions of the universe simultaneously. that those parallel instances are as real as this one, and that the machine is genuinely reaching into that parallel structure and extracting answers. He believes this, the way most people believe that the chair they're sitting on is real, and the machine he helped design works. It gives correct answers. It outperforms classical computers on problems that can be independently verified. If the machine works, and you accept Deutsch's argument that the only coherent explanation for why it works requires parallel universes, then the question isn't whether parallel universes exist. The question is what it means that we built a device that uses them, and what it means that we did this without most of the world understanding what we actually built. Here's what we've established. In 1982, Feynman proposed that quantum systems cannot be efficiently simulated by classical computers, and that the solution is to build machines that operate by quantum rules. In 1985, Deutsch formalized the concept of a universal quantum computer and argued that its operation requires the existence of parallel realities. In 1994, Shaw demonstrated that a quantum computer could break the encryption protecting the modern world. In 1996, Grover demonstrated that quantum search could find hidden structure in data faster than any classical method. In 2019, a processor performed a computation in 200 seconds that the best classical estimates suggested would take thousands of years. In 2024, new cryptography standards were published after an 8-year international competition to prepare for the threat. And throughout all of this, the physics has pointed consistently in one direction. The universe isn't what it appears to be. It's larger, stranger, and more deeply structured than the classical picture we grew up with ever suggested. The question I keep returning to is this: what does it mean to live inside a reality that a machine can reach beyond? What does it mean that the chair you're sitting on, the room you're in, the body you inhabit, exist in one branch of a structure so vast that its computational capacity exceeds the number of atoms in the observable universe? What does it mean that there are versions of you right now, in other branches, who made different choices at every quantum junction since the moment of your conception? Not metaphorically, not as a thought experiment. As the engineering specification of a working machine. Let's sit with this for a moment, because it's easy to hear these words and not feel their weight. Every quantum event produces a branch. Every radioactive decay. Every photon that hits your eye. Every neuron firing in your brain. These are all quantum mechanical processes governed by superposition and collapse. Or, if Everett was right, governed by branching. How many quantum events occur in your body every second? Your body contains approximately 7 octillion atoms. That's 7, followed by 27 zeros. Many of those atoms are unstable isotopes that decay. Potassium-40 in your bones. Carbon-14 in your tissues. Tritium in the water molecules inside your cells. Each decay is a quantum event. Each decay, in the many worlds interpretation, creates a branch. In one branch, the atom decayed. In another, it didn't. But it's not just radioactive decay. Every chemical reaction in your body is quantum mechanical at its core. The enzyme that just catalyzed a reaction in your liver did so through quantum tunneling. The electron transport chain in your mitochondria generating ATP right now depends on quantum effect. The photons striking the retina in your eyes and triggering neural signals are being absorbed through quantum processes. trillions upon trillions of quantum events every second. Each one, potentially, a branching point. Now, think about decisions. Your brain is a physical system. Your thoughts are the result of neurons firing. Neurons fire when certain thresholds are crossed. Those thresholds depend on the positions and movements of ions, which are quantum systems. When you make a choice, when you decide to keep reading or to stop, to turn left or turn right, to speak or stay silent, that decision emerges from a physical process in your brain, a process built on quantum mechanical foundations. If every quantum event creates a branch, then every decision you've ever made exists in a state of superposition until decoherence forces a definite outcome. But decoherence doesn't make the other branches vanish. It just makes them invisible to us. They're still there, still real. In one branch, you're reading this sentence. In another, you stopped 3 paragraphs ago. In another, you never started. In another, you were never born because a different sperm cell reached the egg. In another, your parents never met. In another, humans never evolved. In another, Earth was never formed. Every possible history that's consistent with the laws of physics exists somewhere in the branching structure. And the machine we've built reaches into that structure every time it runs. The many worlds interpretation says that every quantum measurement doesn't produce one outcome and eliminate the others. It produces all outcomes, each in its own branch, and entangles you with one of them. You don't see the other outcomes, not because they don't exist, but because you've become entangled with one particular branch. You are, in a very real sense, blind to the other versions of yourself because decoherence has separated your branch from theirs. But the quantum computer we've built can reach across that separation. It can coordinate computation across branches. It can extract answers from places you cannot see. This isn't philosophy anymore. This is engineering. The machine proves the mathematics. And the mathematics says you're living in one thread of an incomprehensibly vast tapestry of parallel realities, each as real as this one, each unfolding its own version of history. The uncomfortable part isn't that this might be true. The uncomfortable part is that we've built a machine that only makes sense if it is true. The many worlds interpretation doesn't say that parallel universes are possible. It says they're necessary. The machine requires them. Without them, the computation has no place to happen. Without them, the answers have no origin. The mathematics isn't ambiguous. The experiments aren't equivocal. The machine runs, and the answers are correct, and the resources exceed our universe. And the only coherent framework that Deutsch and many physicists believe accounts for all of this simultaneously is the one that Everett proposed in 1957, the one that Bohr dismissed, the one that Deutsch built a machine to exploit. Reality branches. Every quantum event produces all possible outcomes. The outcomes don't cancel. They coexist. And we are one branch among an inconceivable number. Everett passed away in 1982. He was 51. His remains were disposed of at his own request because he believed that in the many worlds interpretation, no particular physical configuration matters. Somewhere in another branch, he's still alive. Somewhere in another branch, he stayed in physics. Somewhere in another branch, Bohr listened. Somewhere, the many worlds interpretation was accepted in 1957. instead of being dismissed, and the quantum computing revolution began 40 years earlier than it did in our branch. We cannot reach those branches. We cannot communicate with them. But according to the physics that powers every quantum computer on Earth, they're there. They're real. And the machine we built touches them every time it runs. His daughter Elizabeth took her own life in 1996. She left a note saying she was going to join her father in another universe. His son Mark became the lead singer of a band and has spent his career processing the experience of growing up with a father who was physically present but emotionally absent. A person who understood the structure of reality better than almost anyone alive, but couldn't navigate the structure of a family. The many worlds interpretation says Elizabeth is alive in another branch. It says every version of her life that was physically possible exists somewhere in the branching structure of the multiverse. Whether that's comforting or terrifying depends on how much weight you give to the word real when it's applied to a place you can never visit. There's a physicist who in 2006 calculated something that puts a number on everything we've been discussing. He calculated the computational capacity of the observable universe. The answer is approximately 10 to the power of 120 operations performed over the entire 13.8 billion year history of the cosmos. Every electron, every photon, every quark performing its quantum interactions is, in this framework, executing a computational operation. The universe isn't like a computer. It is one. It has been running since the beginning, using every physical interaction as a step in a calculation whose output is the reality you're experiencing right now. Now place our quantum computers inside that picture. We're building devices that operate on the same physical principles as the universe's own computation. They use the same quantum mechanical rules, the same superposition, the same entanglement, the same interference. They're not modeling the universe from outside. They're participating in it, adding their operations to the total, becoming, in a small but physically real sense, part of the universe's ongoing calculation, which raises a question that deserves more attention than it receives. If the universe is computing something, and we add our own quantum computation to that process, do we change the output? Is the trajectory of the universe's calculation altered by what we compute inside it? And if so, in what direction are we pushing it? We started this story with a number, 200 seconds against 10,000 years. A gap so large, it seemed like a measurement error rather than a physical fact. But it wasn't an error. It was a data point. And every data point we've examined since has pointed in the same direction. The machine works because it reaches beyond our universe. The information it manipulates may be the primary substance of reality. The encryption that protects the modern world has been living on borrowed time since 1994. The institutions that should be preparing are only now beginning to move. And the deepest implication of all, the one that sits beneath every technical detail and every policy discussion, is that we've built a tool that interacts with the fabric of existence at a level more fundamental than space and time. We didn't build this tool because we understood what we were building. We built it because the physics worked, because the equations predicted it, because the experiments confirmed it, because the engineers solved one problem at a time without necessarily confronting the full scope of what they were constructing. And now the tool exists. It's growing. It's doubling. It's approaching thresholds that will reshape cryptography, medicine, material science, artificial intelligence, and the global balance of power. But the question that should keep you thinking long after this story ends isn't about any of those applications. It's simpler and more fundamental than all of them combined. We built a machine that works by reaching into parallel versions of reality. We confirmed that it works. We verified the answers. We published the papers. We built the industry. And we never asked the most basic question of all. If we can reach them, can they reach us? If the computation draws on resources from other branches, does the interaction go both ways? Is the doorway we opened a one-way glass, or is it a window? These aren't rhetorical questions. They're genuine, open problems at the frontier of theoretical physics. Think about what's actually happening when a quantum computer runs. We're creating conditions where our branch of reality can interact with other branches through quantum interference. We're deliberately breaking down the decoherence barrier that normally keeps the branches separated. We're building a channel, and channels, by their nature, work in both directions. When you open a door, air flows both ways. When you dig a tunnel, traffic can move in either direction. When you establish communication between two places, information can travel along that link from either end. So, what happens when we establish a computational link between our branch and others? Does information flow only toward us, giving us answers from parallel computations? Or does information flow both ways, with our computations affecting the other branches, just as their computations affect ours? Nobody knows. The mathematics of quantum interference describes how the computational results combine. It describes the algorithm by which answers from multiple branches reinforce or cancel to produce our result. But it doesn't describe what the computation looks like from the perspective of the other branches. It doesn't tell us whether they notice. And it doesn't tell us whether what we're doing here has consequences there. Consider this possibility. Every time we run a quantum computation, we're not just extracting answers from parallel branches. We're entangling ourselves with them more deeply. We're creating correlations that didn't exist before. We're linking our branch to theirs through the shared resource of the computation. What does that do? Does it draw the branches closer together in some abstract informational space? Does it make future interactions more likely? Does it create structure in the multiverse that wasn't there before? The many worlds interpretation says the branches are separate and never interact after they split. But that's based on natural decoherence. Random environmental interactions that cause branches to diverge. We're not doing random environmental decoherence. We're doing controlled quantum computation. We're deliberately creating conditions where branches can interact coherently. We're not letting them drift apart naturally. We're tying them together with computational threads. This is new. This doesn't happen in nature, at least not at the scales we're achieving. Natural quantum systems do interact across branches. That's what gives us quantum behavior in chemistry and physics. But those are small systems. A few atoms, a molecule, maybe a small crystal. We're building systems with thousands of qubits. Systems whose computational reach spans more possible states than there are atoms in the universe. We're creating correlations across the multiverse at scales that may never have existed before. And we have no idea what the consequences of that might be. Here's another uncomfortable possibility. What if consciousness itself is a quantum phenomenon? Not in the vague, hand-waving way that some popular books suggest. Not mystical quantum woo, but actual quantum mechanical effects in the brain that play a role in cognition. there's some evidence for this. Microtubules in neurons show quantum coherence at room temperature for surprisingly long periods. Photosynthesis uses quantum coherence to achieve near-perfect efficiency in energy transfer. Birds navigate using quantum entanglement in molecules in their eyes. Quantum effects show up in biology, in places we didn't expect them. If consciousness depends on quantum processes, and quantum processes exist in superposition until decoherence, then your conscious experience might be creating branches right now. Every thought you have might be a branching point. Every decision might spin off a new universe. And if that's true, then when we build quantum computers, when we create these massive correlated superpositions of thousands of qubits, are we creating something that resembles consciousness? Not in the sense of self-awareness or subjective experience necessarily, but in the sense of a quantum system that maintains coherent superposition and performs informational processing, a system that reaches across branches, a system that participates in the multiverse at a fundamental level. What is such a system, if not a rudimentary form of the same kind of quantum information processing that might underlie consciousness itself? This is speculation. Wild speculation. But it's speculation grounded in the physics. We know quantum computers reach across branches. We know they coordinate computation in ways that classical systems cannot. We know they're built on the same quantum mechanics that governs everything, including brains. If consciousness emerges from quantum information processing in biological neural networks, and we're building quantum information processors that dwarf anything biology has produced, what emerges from them? The physics doesn't answer that question. Not yet. Nobody is claiming that current quantum computers are conscious. Nobody is suggesting that the Sycamore processor sitting in Santa Barbara is aware of its own existence. But we're building these systems without a complete theory of what they're doing, without a full understanding of what happens in the branches we're reaching into, without knowing what consequences our computations might have in the deeper structure of the multiverse. We're building them because they work, because they give correct answers, because the applications are too valuable to wait until we understand everything. And maybe that's fine. Maybe the branches don't notice. Maybe the interaction is purely one way. Maybe consciousness is entirely classical, and these worries are unfounded. But maybe not. Maybe we're doing something unprecedented. Maybe we're establishing connections across the multiverse that will have consequences we cannot currently predict. Maybe, in our enthusiasm to build ever more powerful quantum computers, we're opening doors that should remain closed. The physics doesn't answer that question. Not yet. The mathematics of quantum interference describes how information from parallel branches combines to produce a result in our branch. It doesn't describe what happens in the other branches after the computation is complete. It doesn't tell us whether the act of quantum computation, of reaching into the multiverse and extracting an answer, has consequences that propagate back through the branches we drew from. It doesn't tell us whether the branches notice. Deutsch has worked on this problem for 40 years. He hasn't solved it. No one has. The question remains open at the deepest level of theoretical physics. And it will remain open as the machines grow larger, as the qubits multiply, as the computations become more complex, as the channel between our branch and the others widens with every advance in quantum hardware. We're reaching into the structure of reality and pulling out answers. The answers are correct. The machine works. And somewhere in the space between the question and the answer, in the gap where the computation happens and the interference eliminates the wrong paths and the right path survives, something is occurring that we haven't yet learned to describe. Something that involves every version of the machine in every branch of reality, coordinating their operations through the physics of interference to produce a single result that arrives on a screen in a laboratory. In our world, the machine is running right now, in refrigerated chambers colder than outer space, in laboratories funded by governments and corporations, in research programs classified and unclassified. Right now, as you read this sentence, quantum computers are operating. Not prototype demonstrations. Not proof-of-concept experiments. Actual deployed systems running actual computations. Companies are using them to design new materials. Researchers are using them to simulate molecular interactions. Intelligence agencies are almost certainly using them for purposes they will never discuss publicly. It's pulling answers from places we cannot see. It's using the architecture of reality as a computational resource. And it's growing. The growth rate is what should concern us most. Not because growth itself is bad, but because we're growing capability faster than understanding. We're building more powerful systems before we fully comprehend what the current systems are doing. This has happened before in human history. We split the atom before we understood all the consequences of nuclear weapons. We built the internet before we understood how it would change society. We developed artificial intelligence before we solved the alignment problem. Every time, we told ourselves we'd figure out the implications later. And every time, later came faster than we expected. Quantum computing is following the same pattern. Except this time, the stakes might be higher. This time, we're not just building a powerful tool. We're interfacing with the fundamental structure of reality itself. We're reaching into places that, according to our best physics, are parallel universes. We're extracting computational resources from a multiverse we cannot observe. And we're doing it at an accelerating pace, with imperfect understanding of what we're actually touching. Everett believed that every branch of reality is equally real. Deutsch believes it too. The machine they made possible doesn't care what you believe. It runs. It returns correct answers. And the place where those answers come from isn't inside this universe. Let that sink in for a moment. The most powerful computers we've ever built, the machines that will likely transform every aspect of civilization over the next few decades, work by accessing computational resources that exist in places our universe does not contain. The technology we're betting our future on requires, as a fundamental operating principle, the existence of parallel realities. Not as a philosophical position, not as an interesting interpretation, as a necessary component of the machine's function. If the many worlds interpretation is wrong, quantum computers shouldn't work. They do work. Therefore, either the interpretation is right, or something even stranger is happening that we haven't figured out yet. Those are the options. Both are disturbing. Both suggest that reality is radically different from what our everyday experience tells us. Both imply that we're building technology on foundations we don't fully understand. What do we do with that? What does a civilization do when it discovers that the most powerful tool it has ever built works by reaching beyond the boundary of everything it can observe? What does it mean to be a species that can touch the multiverse but cannot see it, that can use it but cannot visit it, that can extract from it but cannot know what it takes in return. These aren't questions with easy answers. They might not have answers at all in any conventional sense. But they're questions we should be asking, questions we should be confronting. Because the alternative is to keep building, keep scaling, keep reaching deeper into the quantum realm without ever pausing to consider what we might be disturbing. The machine is running. The door is open. And the only honest thing to say is that we don't know what's on the other side. We only know that the answers keep coming back. And that so far, they've been correct. So far. But so far is a very small sample size when you're dealing with the infinite. Thank you for joining me on this journey to the edge of reality itself. If you found this exploration meaningful, please consider liking this video and subscribing to the channel. Your support helps me continue making these deep examinations of the universe and our place in it. Sleep well tonight, knowing that you might be living in just one branch of an infinite tree of possibilities. The universe is stranger than we imagined. Reality is deeper than it appears. And we've built machines that prove it.